Now that we've spent a little bit of time studying both gravity and electrostatics, one thing I'd like to do is spend just a little bit of time making some analogies between them because they're very similar in a lot of ways. So to begin with, Coulomb's law, which says that the electric force equals K Q1 Q2 over R squared, is almost the same in form as Newton's law of universal gravitation, which tells us that the gravitational force is equal to G m1 m2 over r squared. So because these two equations are so similar, it makes sense to spend a little bit of time seeing what's the same and what's the difference between them. Okay, so one thing that we can immediately see is that the forces are, on the left-hand side in both cases. Okay, so the gravitational force and the electric force are analogous to each other in that way. We can also see that mass is the gravitational equivalent to charge. Okay, so electric charges are this material property that tell us how strong the force between two objects is going to be. Similarly, mass is this gravitational property that tells us how strong the force between two objects are going to be. So we can think of mass as being like charge. They play the same role in these two equations. We also see that the relationship with distance is the same. So both follow an inverse square law. Okay, so as you get twice as far away, each force becomes 4 times weaker. The forces go to 0 as you go to infinity. We can also compare the constants, and although comparing kilograms to coulombs is totally arbitrary, we still find that for some, reasonable, test case, like say you compared the force on 2 protons or the force on a proton and an electron, what you find is that the constants are pretty different. So, the force that we get for the electrical attraction, say, between a proton and an electron is so much larger than the gravitational force that it is hard to imagine that we could ever even measure the gravitational force in those cases. So, in fact, the gravitational force is 10 to the 39 times weaker than the electric force between an electron and a proton. Okay, and you can do this calculation really easily. Just plug in the gravitational force between 2 protons. Just take the mass of a proton and do the calculation at some distance, say a meter apart. And then do the same calculation with the electric force between 2 protons or between a proton and an electron. And you'll see that the gravitational force is just dramatically smaller when you make that comparison. Okay, and that relationship shows up in the constants out front. Okay, so there's another difference between these, and that difference is that while gravitational forces are always attractive, electric forces can attract or repel. Okay, so don't be confused by the fact that these two forces have the same form. There are some qualitatively very different behaviors because of that fact. There's another thing that I want to draw your attention to, which is if we calculate the force on one of these objects, like let's say we have a gravitational force between a planet and a moon, and we calculate the, let's say, acceleration of the moon. Or let's say we have an electric force between a proton and an electron, and we calculate the acceleration of the electron. Something kind of strange happens because of Newton's second law. So Newton's second law tells us that the force on an object equals the mass of the object times its acceleration. So the fact that mass shows up in Newton's second law and also shows up in Newton's law of universal gravitation means that the behavior, the actual motion of an object that's behaving under gravity is qualitatively different than the motion of an object that's behaving under an electric force. Because if I double the mass of an object, then I both double the gravitational force and double its inertia in Newton's second law. But if I double the mass of an object under electrical forces, that will not affect the force at all. It'll affect the acceleration only. Okay, so this kind of peculiar relationship that mass shows up in these two pretty different equations is known as the equivalence principle. And essentially, we relate the inertial mass, which is the one that shows up in F equals ma, and the gravitational mass, which is the one that shows up in Newton's law of universal gravitation. And all experiments that we've ever done indicate that those two masses are consistent with each other. There is no difference between them. Even though, from a theoretical perspective, there's not a lot of reason to think they should be. It would make perfect sense for those two masses to be different. Maybe one object could have a larger inertia, but another one could experience a larger gravitational force. In practice, we do not see that. In fact, there's a third part to the equivalence principle, which is what we call the relativistic mass. So you've probably seen from pop culture the relationship that E equals mc squared. So the energy of an object, the mass energy, the rest energy is proportional to its mass. And so that shows up in various cases where, for instance, in nuclear reactions, some mass may be turned into kinetic energy. We see that there's a mass that shows up here, and again, that seems to be consistent with the gravitational mass and with the inertial mass. All right, so this was one of the inspirations to general relativity, which goes way beyond what we can do in this class. But the fact that these three kinds of masses, which all show up in totally different areas, but are all seemingly the same quantity, is one of the mysteries that is something that seems to be really important for modern physics. Okay, so what I'd like to do is talk about, is there a gravitational analog for other things? So we found that mass is like charge, the gravitational force is like the electric force, but, oh goodness, is there a gravitational analog to E? Okay, well, so remember that the electric field is defined to be the electric force divided by the charge. Well, if I want to do this with gravity, then I say, okay, is there some quantity that I get when I take the gravitational force and I divide it by the mass? And we can see, yes, that is a thing that shows up in 121 all the time. That's just g. That's the acceleration due to gravity. But notice that we have a vector on the right-hand side. So now we have g vector, which is just the gravitational force divided by the mass. Okay, and we call this the gravitational field, in analogy with the electric field. And what this represents is just simply which direction an object will fall and what acceleration it will have when it falls. Okay, so I can sketch out the Earth like so. And if I want to draw the gravitational field around the Earth, then I can draw it kind of like this, pointing towards the Earth in all directions. And if I go further away, then there will be a weaker gravitational field, but still pointing towards the Earth. Okay, so this is very similar to what the electric field looks like for a negatively charged object. And we can think of this in much the same way that we think about electrical fields. So this is, again, an invisible structure. That extends from objects with mass and is an agent by which the objects can tell that there's some force they should be experiencing. It's the way that massive objects interact with each other. And then again, according to general relativity, we can think of this as even more concrete than that. We can think of this as a warping of space-time. So you can almost imagine a gravitational well, we call it, around a planet where objects are being sort of pulled in because there's this sort of low spot in the gravitational well. The curving of the structure in space causes objects to want to be deflected in their motion towards the planet.